So let us start with the topic, that is T and L beams. Okay, so far we have done in limit state method, we have done the introduction, we have done the singly reinforced, we have also done the doubly reinforced beams. So after doing singly reinforced and doubly reinforced rectangular beams, okay, we have already done rectangular beams. After that, we are going to start with T and L beams. So let us see what are actually T and L beams. So you know that in RCC construction, beams and slabs are generally they are cast monolithically. Okay, what do you mean by monolithically? They are cast at the same time. So the stirrups and the bent up bars of the beam extend into the slab, and a portion of the slab acts with the beam for resisting compressive stresses. So basically what happens, a portion of the slab with the beam also it acts to resist the compressive stresses. So this results in increasing the moment of resistance of the beam. So the slab portion is called as the flange, and the beam portion is called as the web or rib of the beam. Okay. So here you can see the cross section. This is the cross section of a beam slab construction. So this corner beam, so this is the beam we are talking about. So here you can see this is the thickness of the slab, and this is your actual beam. But while taking the loads, okay, the behavior of this portion, it is not going to be like that only this beam will bend due to the loading. ठीक है, इसके ऊपर वॉल भी रहेगा. So ऐसा तो नहीं होगा कि सिर्फ इतना ही पोर्शन बेंड होगा, इसके साथ में this slab portion will also bend. Am I correct? So that together we are considering it this whole as a beam. So now since this whole it makes a shape of an alphabet T, so hence it is also called as a T beam. Is this clear everyone? ये जो shape दिख रहा है, it is the shape of an alphabet T. तो इसी के लिए इसको T beam भी बोलते हैं. Or you can say this as a flange section. ठीक है, what is flange? Flange is nothing but the depth of the slab. ठीक है, जो flange portion है, that is nothing but the slab portion. So now if you come to this corner portion, so at the कोई if you consider a plan, center जो beams है that will look like this in the shape of a T. But what about the beams at the corner? So at the corner you will find the shape like this. So now this, since this shape resembles the letter T, letter L, it is also called as the L beam. So in this case, this will be the width of the flange, BF. For this beam, this will be the width of the flange, and for this T beam, this will be the width of the flange. Yes, so these are the components of a T beam. So this portion is called as the web of the beam, or it is, you can also say it as the rib of the beam. और ये जो portion है, this is called as the flange of the beam. ठीक है, BF is nothing but the effective width of the flange. ठीक है, when I say only B, that will be the actual width of the flange, and when I say BF, you can say that it is the effective width of the flange. Yes, this much is clear to everyone. Yes.
Yes, sir.
Okay, so let us move ahead. So now see, where BF is the width of the flange, BW is the width of the rib, and DF is nothing but the depth of the flange or the depth of the slab. So I hope this figure is clear to all. Okay, so let us see some more figures so that you will understand what is actually a T beam. Okay, so in this figure, can you see a 3D figure of this so that you understand what exactly we are talking about? Okay, it's a 3D view of a beam slab construction. So here you can see this portion is what we are dealing with. This is called as a T beam, and this is called as the L beam. Okay, this B is the width of the beam. Let us say S1, S2 is the span of the slab. ठीक है, और ये जो span है, ठीक है, I hope you can see my cursor. This span is the span of the beam. ठीक है, this is the span of the slab. Is this clear everyone? Yes or no? Is this clear?
Yes, sir.
Okay, fine. So now let us see some more figures of this so that you understand. Okay, so this we are talking about. So this portion is called as the flange. So as I've already told you, so this portion actually takes part in actually resisting the compressive stresses on this beam. ठीक है, तो इतना portion act करेगा to resist the stresses. So that's why we have shown this in different color. So this whole we will consider it as a beam. So that beam is nothing but your T beam. So this is called as the web, this is the L beam, this is the slab, this is the flange. These are the components of a typical T and L beams. Is this clear? ठीक है, so this is the span from the center to center. ठीक है, one more figure we will see. So how it will deflect due to the loading. So this is the initial shape of a T beam. ठीक है, so once subjected to loading, it will bend like this. So this portion will also bend with this. Are you getting? That is the reason we are considering this entire thing as the part of the beam, and that beam is nothing but your T beam. Yes, is this clear, everyone?
Yes, sir.
Okay. So now tell me. So since this is a T beam, so how to the next important thing in this, once you understand what is a T beam, the next important thing is you should understand what is the effective width of a T beam. Okay. So now if you see here the deflected shape of a T beam, so in this, once subjected to loading, it will try to deflect like this. So how much width should we take for this T beam? We are considering this as a T beam. We know that some portion of the slab will also behave as of the beam while subjected to loading. So how much width of this T beam we should consider? So that is the question. Correct? So ये width मैं कितना ले सकता हूँ? Suppose I have this slab. So we have actually stopped here. So can I take till here also the width of the flange? Till here also. So how to know that? How much is the width of the T beam? Yes, anyone can tell me how much should be the width, and it depends on what actually. Yes, this width of a T beam,
Distance between two supports.
distance between two supports. Yes, so in this example, so can I take this width and increase and take till here also? So now
Yes.
tell, yes, I can take this width of the flange. Okay, so I can increase this like this. Yes or no? Anyone? ठीक है, the next
Yes, sir.
important thing is to decide the width of the flange. Width of the flange कितना consider करना है? Suppose ये तो S1 है. Suppose it is the span is even bigger than this. So in that case कितना consider करेंगे? So that remains a question mark. So the width of the flange is decided. So I told you there are two widths. One is only the actual width of the flange and the effective width of the flange. Okay. So in this case, the actual width of the flange is taken as this S1, the span. Suppose this span is from the center of the beam. Okay, center of the beam to the center of the beam, let us say L1, ये slab के लिए, and this slab let us say L2. So in that case, the actual width of the flange will become, okay, pay attention, the actual width of the flange will become L1 by 2 plus this B will remain as it is, width of the web, B plus again, sorry, again L2 by 2. Is this clear, everyone? This is called as the actual width of the flange, and BF is nothing but your effective width of the flange. So your effective width of the flange will always be less than your actual width of the flange. Is this clear, everyone? Yes or no?
Yes, sir.
Okay. So now, why we are actually taking this effective width less than the actual width? Anyone can just tell me whatever you feel, even though if it is wrong, doesn't matter. We're trying to understand the concept, so you can express yourself. That is not a problem. Yes, did you understand my question? Why are we taking this effective width less than the actual width?
Somewhat like under reinforced and over reinforced.
Somewhat like under reinforced and over reinforced. Not exactly. Yes, still people are just typing their attendance. I I am expecting some answers from you. Okay, so now this effective width of the flange, as I have already told you, is always less than the actual width. So now why we are taking this less than the actual width? Consider this portion. So suppose we are taking the width of the flange till here. So now as I increase this width of the flange, now tell me what will be the load carrying capacity of this web. Okay, so as I move away from the web, the load carrying capacity will increase or decrease? It will decrease, right? As I move away from the web, if I come here, so this portion will take less load. Okay, we are actually placing the wall right above the beam, right? So the beam will take the load of the wall. So now as we move away from this web, the load taking capacity of this flange will reduce. So at this point it will actually not take any load, it will actually bend. So that is the reason we are restricting the width of the flange to a particular value for the analysis of the beams. So as we move away from the web, the load carrying capacity of the slab will decrease as the compressive stresses. So that is the reason we are actually keeping this effective width always less than the actual width of the T beam. Is this clear, everyone?
Yes.
Okay, fine. So now let us move ahead. Since you already know what is the effective width of the flange and the actual width of the flange, now let us see what is the equation for the effective width of the flange. So now here you can see the width of the flange. The effective width of the flange may be taken as follows, but in no case greater than the center to center spacing of the beam. Okay, so this is actually given in IS code also. So this effective width of the flange, when it is not given to you, you will have to find out by this equation, L naught upon 6 plus BW plus 6 times DF. So you already know what is DF. DF is nothing but the depth of the flange or the depth of the slab. BW is nothing but the width of the web, that is width of the beam. And L naught, L naught is what? The distance between the points of zero moments, or you can say L naught is the distance between the points of contraflexure. So what is the point of contraflexure? Is nothing but point of zero moment. Okay, and for this again, this L naught they have separated for two cases. For continuous beam it is taken as zero point 0.7 times L effective, and for an isolated beam, for a simply supported beam, you know that the distance is from the zero bending moment only. So in that case there is no issue, simply supported beam ka total length aa jayega, correct? So this was the equation for the effective width of the flange for isolated beams. Okay, for isolated beams it is this is for the continuous beam. So in some cases there is a possibility कि only एक single तुम्हारा T beam है, so that will be your isolated T beam. So in isolated T beam, BF is given by L naught upon B plus 4 plus BW. ठीक है. So remember this I have mentioned, where b is the actual width of the flange. We just talked about that. Is this clear? So now let us see what is L naught in case of continuous. Okay, so L naught, so let us say this is a continuous beam slab. So in this the bending moment will be like this. So in this case, how to take L naught? So this is the point of zero bending moment and this is the point of zero, and again it is going into hogging. So this will be your L naught. So I have just shown you this, how to take L naught in case of continuous beams. Is this clear? L naught. So this is actually the plan of a slab, and this is Lx and this is Ly. So this is the main steel. So when the main steel is parallel to the beam, so in that case, this transverse reinforcement, we should take at least 60 percentage of the steel in the mid span. So that is the criteria given in the IS code. Okay. So everyone understood this, the width of the flange, and for continuous and for isolated. That is important. I hope this is clear to everyone. Yes.
Yes.
Okay. So let us actually just see the IS code also. So in IS code where it is mentioned T beams, anyone? So if you see this, you will find T beam here, clause number 23.1. Okay. So you should actually always refer the IS code. It is always better. So page number 36, if you see, we will find some introduction of the T beams also. So here you can see clause 23.1 T beams and L beams. So here it is mentioned a slab which is assumed to act as a compression flange of a T beam or L beam shall satisfy the following condition. So these are the conditions it should satisfy to consider it as a T beam or a flange beam. The slab shall be cast integrally. We have just discussed the slab should be cast monolithically with the beam. So that is given. And the second thing is, if the main reinforcement of the slab is parallel to the beam, transverse reinforcement shall be provided. Such reinforcement shall not be less than 60% of the main reinforcement at the midspan of the slab. Okay, did you understand this? This is what I was showing you in the PDF. Okay, so the second condition actually I've shown you with the help of this figure. So what the second condition is saying, it is saying that if the main bars are parallel to the beam, ठीक है, suppose here it is a beam, तो ये main bar तुम्हारा short along the short span रहेगा slab के, ठीक है, this is LX, तो main bars is along the short span, तो ये जो beam है उसका और ये steel दोनों parallel हो गया. So in that case we have to provide this transverse reinforcement on the upper side such that it should not be less than 60 percentage of the steel at the midspan. Okay, so that is what is mentioned here. So that is what I have shown you with the help of the figure. So now let us see what is the effective width of the flange. So in the absence of more accurate determination, the effective width of the flange may be taken as the following. So here the equation is already given to you. So for T beams also it is given, for L beams. T beam we have just seen, it is L naught upon 6 plus BW plus 6 times DF. For L beams also it is given. For isolated T beams के लिए भी T and L के लिए it is already given. Okay. So I hope this is clear to you. So now let us move on to the next part. So this we have already seen, this we have already seen. So now let us come to the most important part, the equations of the T-beam. So these are the equations. So now on the basis of this, once we understand these equations, then only we can start with the numericals. So that is the reason we will complete this and then we'll start with the numericals. So in this, there are actually three possibilities. Whenever we analyze a T-beam, understand there are three possibilities. So what is that? We will see that one by one. So the first possibility or the first case is your neutral axis lies within the flange. That means your XU is less than DF. That is the first possibility. Since now we are dealing with a T beam, so there might be a possibility जो neutral axis है, it will lie either here or it will go beyond this flange. So that is the reason we have conditions. So the first condition is xu is less than df. So in the figure you can see this xu, it is lying inside the thickness of the flange. So did you understand the case, the first case, what I'm talking about? xu is less than df. df क्या है तुम्हारा? Depth of the flange. Yes, is this clear everyone?
Yes, sir.
Okay. So now let us see this stress diagram you already know. So this is the total compressive force which is acting at 0.42 xu from the compression fiber. This is the stress value 0.446 fck, and we are first dealing with the balanced section. So I have written xu equal to xu max, and this is the lever arm d minus 0.42 xu max, and this is the tensile force. So now let us see, for a balanced section we know that xu is equal to xu max. So now MR is given by CU into lever arm or TU into lever arm. So it is given by 0.36 FCK B. So remember, B is nothing but, in this case it will become the width of the flange, BF. Okay? So this is the only change. The rest of the equation remains the same. 0.36 FCK B into XU max into D minus 0.42 XU max. So this is the equation for MR for a balanced section. Or so if you simplify this, you can directly write like this. This we have already done this in singly and doubly reinforced. So for Fe250 it will become 0.148 FCK BD square. B is nothing but BF. Okay, make a note of this. So whenever we are talking about this equation, you can quickly make a note of that. And then for Fe415, MR is 0.138 FCK BF into D square, and for Fe500 it is 0.133. Okay. So now let us talk about the under reinforced section. So now for under reinforced section, we know that xu is less than xu max. So same figure I have drawn. So first for under reinforced section, we will find out xu. So how to find out xu? Again the same equations equating cu equal to tu. So cu is nothing but 0.36 fck. ये हो जाएगा bf into xu. Tu is nothing but 0.87 fy into ast. So from this we can find out xu. Xu max we already know. For different grade of steel it is different. Excuse me. Okay. So if xu is less than xu max, we know that it is an under reinforced section. So now how to find out MR? So in this case, MR is simple, either Cu into lever arm or Tu into lever arm. So 0.36 FCK BF into XU into lever arm, or TU के लिए 0.87 FI into ST into lever arm. Is this clear everyone? First case clear हो गया. When XU is less than DF, it is similar to the rectangular beam only. The only difference is B के जगह पे BF. I hope this is clear. Yes.
Yes, sir.
Okay, fine. So now let us move on to the second case. Very interesting. Second case is interesting. So the second case says that XU is greater than DF and DF is less than 3 by 7 XU. So we already know that while we did the stress block parameters, we know all these things of a stress diagram. So this rectangular portion is 3 by 7 xu, the depth of this, and then this parabolic portion is 4 by 7 xu. We have already derived all these things. So I hope you know this stress diagram. So the second case says that, sorry. Yes, the second case says that your xu is lying is greater than df. So here you can see my xu is greater than df. See, this is my xu, and df is less than 3 by 7 xu. So again, there is one more possibility that this depth of the flange is less than 3 by 7 xu. 3 by 7 xu क्या है? This rectangular portion. Yes, are you getting this condition? Is this clear everyone? Yes or no?
Sir, tell it again.
Sorry.
Explain it again.
Okay. So first try to understand this figure. Okay, pay attention all of you. So this is your T beam. So what I have done, okay, I have just marked this web total web portion as area 1 and the flange portion as area 2. So before that, understand the stress diagram. Stress diagram, we already know that this is the 0.446 FCK, the width, and this we have stress block parameters we have derived that this depth till the rectangular portion, it is nothing but 3 by 7 XU, and for this parabolic portion, it is 4 by 7 XU. So the second condition says that your XU is greater than DF. ठीक है, ये DF है मेरा और ये XU है. This XU is greater than DF matlab it is lying beyond DF starting from the compression edge. ठीक है, XU is lying beyond DF मतलब it is greater than DF. और second condition क्या है कि DF is also less than 3 by 7 XU. 3 by 7 XU is nothing but this rectangular portion as I've already told you. तो DF देखो ये जो depth of the flange है इससे छोटा है, इससे less है. See I have drawn this. Now it is clear everyone.
Yes, sir.
Okay, so in this you will have C1 and C2. So this is CU1 for I have separated for area 1 and area 2. ठीक है, CU1 we already know it lies at 0.42 XU from the top fiber and the lever arm distance is D minus 0.42 XU, and the second force for this area will be right at the CG of this thickness. ठीक है, तो ये thickness कितना है DF, तो it will act at the center, तो ये क्या हो जाएगा DF by 2. Now for this, the distance will be, the lever arm will be d minus df by 2 for CU2. I hope this is clear. So now let us see, in this case, for a balance section, in this case, for a balance section, df is less than 3 by 7 xu. So for a balance section, we will check, we know that xu equal to xu max. And if df is less than 3 by 7, then we have to use this formula for MR. So in this case, MR equation will become what? So MR will become Cu1 into lever arm 1 plus Cu2 into lever arm 2. Correct? So Cu1 is nothing but 0.36 FCK BW into XU max into D minus lever arm मैंने अभी बताया. For Cu1 it is D minus 0.42 XU max. Now Cu2 is nothing but 0.446 FCK B into DF. ठीक है? So remember this total BF minus BW, we will get the second area. Are you getting BF minus BW? ठीक है, ये टोटल BF है, इसमें से मैंने BW माइनस किया तो मुझे सेकेंड एरिया मिलेगा. So this we are doing for the second area only, CU2. So I have separated like this so that you understand. I have differentiated with two areas so that you understand this equation. So this will become 0.446 FCK into BF minus BW into DF. ठीक है, ये एरिया हो जाएगा this into DF into lever arm distance क्या है d minus df by 2. Here you can see the lever arm distance is d minus df by 2. So this will be the equation for a balanced section. So again now if you simplify this for different grades like we have already done in singly and doubly reinforced, it will become 0.133 fck bd square plus ये वाला simplify करेंगे तो ये हो जाएगा point, first part simplify करेंगे तो it will become this. ठीक है, only the second part is 0.446 FCK BF minus BW into DF into D minus DF by 2. For Fe415 only this part will change 0.138 FCK BD square, and for Fe250 it is 0.148 FCK BD square. So now remember in this when I'm talking about the CU1 compressive force, so this BW we have taken. ठीक है, because CU1 में क्या है तुम्हारा width क्या है BW है. Are you getting? So that is how it is BW we have taken here. और यहाँ पे ये width find out करने के लिए total BF minus BW करेंगे तो ये मिल जाएगा. Yes, I hope this is clear to everyone. very simple. If you differentiate this like this, then it is very easy to understand. Is this clear, everyone?
Yes, sir.
Yes. Yes, what about others? Everyone, I hope everyone is paying attention, listening to the lecture. Okay. So you want me to zoom this, or is this fine? Okay, which part you're talking about? You want an enlarged view of that diagram? Okay. Okay, I hope this is clear now. So this was the second case when XU is greater than DF and DF is less than 3 by 7 XU. Okay, so now can anyone tell me what can be the third case? So I've already told there are three cases in this. Just can anyone tell me, by we have already done the first and the second, what can be the third case? Okay, since I think the last 1 minute is remaining, so the session will end. We will continue in the next session right at 10 o'clock. Okay, after 10 minutes.